Hey, good morning, good afternoon, and good evening. Thanks for hearing my presentation. Today, I want to introduce about my research, the model that integrates machine learning and process simulation to estimate the energy and greenhouse gas emission of activated carbon production process. Let's talk about activated carbon first. It is a type of carbonaceous material with very high porosity and surface activity. People always use them to absorb the pollutants in the air and water. We can see in this figure, activated carbon can absorb different types of chemicals, especially the metals in the water. Besides, it can also be used to amend the soil, used as the catalyst in the chemical industry, and even the materials in the supercapacitor and batteries. These applications lead to a very high market demand of activated carbon, as we know that the global annual activated carbon demand is over 10 million tons and still keeps growing. So the production of activated carbon, it will consume huge amount of energy and generate greenhouse gas emissions. We are interested in the production process of activated carbon from coal and biomass. The coal is cheap, but it is not renewable. So currently the focus moved to the biomass-based activated carbon. The production process can be attributed to both physical and chemical activation. In the physical activation, we try to pyrolyze the biomass to produce the biochar, and then the biochar is activated by the activation agents like the steam, nitrogen, and carbon dioxide in the inert atmosphere to produce the final activated carbon. In the chemical activation, we use the chemicals to impregnate the biomass first, then do the pyrolysis and the washing. For these processes, lots of people have used experiments to see their results. However, by reviewing their studies, it is hard to find a way to simulate the activated carbon production in different conditions. Their studies focused on the operational conditions, and the influence of biomass feedstocks has rarely been focused. Also, most research pays their attention to the activated carbon product yield and quality, while the process energy consumption and greenhouse gas emissions are lagged. For these reasons, I want to see if we use different types of biomass to produce activated carbon, what kind of effect will happen to the whole activated carbon production process? Will the energy consumption and greenhouse gas emission increase or decrease? If we can find some rules in guiding this feedstock selection or the process optimization, based on this thought, I have established the model for the activity carbon production process. And here is the overall framework for the steam activated carbon production. We At first we pyrolyze the woody biomass to produce the biochar and the gaseous products. The biomass, the biochar is then activated by the steam from the boiler to get the final activated carbon and the flue gas. The gaseous products from the pyrolysis, it is combustible, so we try to assume two different types of scenarios, RE and NRE. RE means we combust this pyrolysis gas along with the natural gas that provides energy, and the NRE means this part of gas are not combusted. In this framework, we have taken the feedstock characterization, the operational conditions for pyrolysis and activations as the input parameters. And based on the output parameters, we can get what our desired, the overall and the detailed energy consumption data, the carbon footprint, and the the product composition of both solid and the gas products. In order to formulate this model, we have tried to integrate different types of technologies like artificial neural network, the pyrolysis kinetic model, and the Aspen Plus simulation. Now let's look at the details of them. I have tried to establish the artificial neural network model, one of the popular machine learning technology, to predict the overall yield and the BET surface area of the produced activated carbon. The reason I use this model is that it can um, do the accurate prediction based on the training for the enough training data. Even we don't need to understand the mechanism of the chemical mechanism of activated carbon production process. Here we have take all these parameters include feedstock characteristics and these operational conditions as the input to predict the yield and BT surface area of the final activated carbon products. We have collected a large amount of data from the literature, and this neural network has been already published in 2019. Since we use artificial neural network to get the yield of the overall process, the detailed product composition, we need to use other types of models for both the pyrolysis and
Mhm.
activation unit. For the pyrolysis unit, we try to use the pyrolysis kinetic model based on the mechanism proposed by Renzi in 2008. They have assumed that the woody biomass its reactions include the reactions of cellulose, hemicellulose, and lignin. A larger amount of reactions is established, and along with the kinetic parameters of these reactions. And so if we just need to know the K, N, and E for each of these reactions, then we can predict the detailed yield and the composition of the pyrolysis process. Like we can even get the elemental composition of the biochar for products in the gas like carbon dioxide, methane, carbon monoxide, and hydrogen. This model is easy to use and have been updated for over 10 years, and that's the reason we select this model. For the activation model, we don't have lots of studies, and we try to assume this reaction for the activation unit. It is based on derived from a linear regression of the experimental data. For the extent of this reaction, it can be calculated based on the predicted yield from artificial neural network and the pyrolysis yield from the previous kinetic models. So based on this model, we can have the condition to simulate the overall steam activated carbon production process. And this simulation is established in the Aspen Plus simulation based on these assumed parameters. So back to our objective, what we are doing in this work is to compare the simulation results between different scenarios with the same operational conditions and different biomass samples. To do this, we firstly collect the characterization of different woody biomass from literature and some databases, and we use this our model to simulation each of them with the assumed operational conditions and do the analysis based on their data, the simulation data. It is expected that we can get the variability of energy consumption and greenhouse gas emission of the production process, how the biomass composition affects them. And also, in order to compare the importance between feedstock characteristics and the operation conditions, we also take the sensitivity analysis. And now let's see the result from this work. Here is a table that shows the correlation coefficients and the accuracy of our established artificial neural network. We can see that in predicting the activated carbon yield, this model have a very high correlation coefficient, and so it is accurate enough for our further simulation works. Here is a figure that shows the energy consumption of the steam-activated carbon production for 7 typical woods with their average result. We can see that most of the energy is used in the pyrolysis, some in the activation, and the remaining used for generating the steam. We can see their average energy consumption is range from 60 to 90 megajoule per kilogram of activated carbon, and the energy recovery from burning the pyrolysis gas can recover around 30 megajoule per kilogram of energy consumption. Here is a figure that shows the carbon footprint of these selected woods. Their values are also very consistent from 6 to 9 carbon dioxide equivalent per kilogram of activated carbon. This greenhouse gas can be divided into fossil-based and biogenic greenhouse gas. Biogenic means this carbon comes from biomass, while the fossil-based means non-biomass derived carbon emissions. The energy recovery here, it can increase the amount of biogenic carbon dioxide and reduce the fossil-based greenhouse gas emissions. Let's see the statistical result for all of the simulations. We can find some interesting things from this table. The average energy consumption and the greenhouse gas emission of the hardwood is smaller than that of the softwood. And if we, with the energy recovery, 1/3 of the energy can be reduced, half of the fossil-based greenhouse gas can be reduced, and the biogenic greenhouse gas it increased for 1/3. Also, we can see a large variation of these results. For example, with the smallest value of the energy consumption of steam-activated carbon production with energy recovery, it is around 23 megajoule per kilogram of activated carbon, while the largest value is 207, 9 times than the smallest value. This finding shows that the importance of the biomass properties to the steam-activated carbon production. So we have tried to correlate the process energy consumption to the biomass composition. We can find some interesting result here. When the hydrogen content or the hydrogen to carbon ratio increased, the process energy consumption it increased a lot. This phenomenon may be explained by the decrease of yield. When the hydrogen content in the biomass is high, the ratio of aromatic carbon in the biomass becomes lower. This aromatic carbon is the skeleton of the final activated carbon, so the yield it will decrease. Since we use the unit as the megajoule per kilogram of activated carbon, the relative energy consumption it will be increased. Besides the energy consumption, you can also see the change of energy recovery in the process if we burn the pyrolysis gas. We have defined this parameter, the energy recovery ratio, to see the amount of energy that can be recovered. We can see that the increase of oxygen content or the oxygen to carbon content, it will make the energy recovery ratio more higher. Our explanation is that higher oxygen in the biomass increases its reactivity, then we can get more gaseous product from the pyrolysis. And so the energy recovery ratio it will be higher. We can summarize some rules of the biomass composition. We can use biomass with lower hydrogen content and higher oxygen content, and so the process energy consumption in producing activated carbon can be decreased. Now we can note the importance of the biomass properties in the process energy consumption, and we also want to compare it with the operational conditions. Here we did the sensitivity analysis to make the comparison, and here is the result. We can see that the relative importance of hydrogen content and ash content is very significant, as well as the impact of the activation temperature, especially when the hydrogen content goes to the upper bound, the energy consumption it increased a lot. Now let's conclude off this result. At first, we have proposed the modeling frameworks that integrate machine learning, pyrolysis kinetics, and Aspen Plus simulation for the steam-activated carbon production. It may be extended to other types of process. Then we do the simulation for different types of woody biomass. We summarize the variability and the distribution of process energy consumption and carbon footprint. The biomass properties have a large impact to them. We can select the biomass with lower hydrogen content and higher oxygen content to reduce the process energy consumption. The sensitivity analysis also tells us before we design the activated carbon production plant, the pre-selection of the biomass feedstock is also very important. And that's all of my presentation. Thank you very much.